Hello and welcome, my MathCounts people. We have the last workout from the 2026 book. This is workout number 6. Let's do it. First problem. If x and y are positive integers that satisfy 2 to the x plus 4 to the y equals 1024, and 4 to the x plus 2 to the y equals 256, what's the value of x plus y? All right, so what I'm going to do is I'm going to change everything in this one to a base of 2. I've got 2 to the x, and I've got 2 to the 2y. So 4 is 2 to the second, so this would be, in my power rule, I'd have 2y. And then this is equal to 1024 is 2 to the 10. Okay, since we're multiplying these two, the exponents are added together. So on this side of the equation, I would have 2 to the x plus 2y is equal to 2 to the 10. So since the bases are the same, the exponents must also be the same. So I can write the equation x plus 2y equals 10. All right, let's move on to the second one. This is 4 to the x, so that would be 2 to the 2x. Times 2 to the y, and then 256 is 2 to the 8th power. So I changed everything to the same base. I'm going to do the same thing over here. We're multiplying like bases, so we add the exponents. We get 2 to the 2x plus y equals 2 to the 8th. And now we can set these two equal to each other. We get 2x plus y equals 8. All right, I want to find out what x plus y is, and I notice something going on here. If I stack these two equations together and add them, I end up with 3x plus 3y. Why did I write 36? 3y, well, I was thinking of the answer, equals 18. So I've just added those two equations together. I want to know what x plus y is. This is 3x plus 3y. So we will divide everything by 3 using the division property of equality. And I get x plus y equals 6. So x plus y is 6. Why did they make this into a calculator problem? You don't need a calculator. Dorina rolls a fair 6-sided die. The number she rolls equals n. What is the expected value of n factorial? Okay, so we've got a die and we don't know what she's going to roll. Okay, and we want the expected value of n factorial. Okay, so here's what we got. We've got the possibility that she rolls a 1. And then that means 1 factorial, because she rolls a 1. And that would be n factorial. And what's the expected value for rolling a 1? Well, 1 out of the 6 would be 1 factorial. So the expected outcome would be 1/6 for that one. Now, if she rolls a 2, it would be 2 factorial times 1/6, the expected outcome, which would be 2/6. If she rolls a 3, that's 3 factorial. And 1/6 of the time she would get that. So that's 3 times 2, that's 6. So we got 6/6. For a 4 factorial, because n is her rolling a 4, that would be 3 times 2 times 4, so that's 24. And then a 5, you would get that 1/6 of the time. So we're doing the total amount we would get from the die roll times the probability of getting that die roll. Does that make sense? So these are the probabilities of us getting it times what we would get for that die roll. So for a 5 die roll, we get 5 factorial. Sorry if I didn't make that clear. 24 times 5 is 120. Losing my mind. And then finally, 6 factorial. If I roll a 6, I would get 6 factorial, but I would only get that 1/6 of the time. That's what expected value means. So 6 times 120, 720, divided by 6. Okay, so all these numbers are divided by 6. So what I can do is I can just add all these numbers together and then divide them all at 6 at one time. So that's what I'm going to do. I'm going to do 1 plus 2 plus 6 plus 24 plus 120 plus 720, 720. And then I'm going to divide them all by 6 at the same time. So when I add all those numbers together, I've already done it. I end up with 873 divided by 6. So that's why I didn't reduce these, because I knew I was going to divide all of them by 6. And this one says express your answer as a decimal to the nearest 10th. So on a calculator, if you plug this in, it comes out to about 145.5. And that's our answer. Next one. Let a sub 1, comma a sub 2, comma a sub 3 be a sequence where a sub 1 is 1. For each integer where n is greater than or equal to 2, the term a sub n is defined as the product of all previous terms plus 2. Okay? What is the units digit of a sub 2025? So basically in this sequence, what is the 2025th term of the sequence going to be? All right, so on problems like this where we're trying to find something way far out in the future, we are going to end up looking for a pattern. Okay, so we already know that a sub 1, the first term of the sequence, is 1, they told us. A sub 2 is defined as, so any integer bigger than 2, is defined as the product of all previous terms plus 2. So the product of 1 plus 2, the second term has to be 1 plus 2, 3. The next term, a sub 3, is the product of these terms over here. 1 times 3 is 3, plus 2, 5. The fourth term, we would take the product of all these terms, 15, and add 2. We would get 17. Now we're looking for the units digit. This would be a 7. Okay, now I do 15 times 17, which comes out to 255, and then I would add 2. So the next number would be 257. Oops, 57. The units digit is 7. And now we should see a pattern at this point. Since all of these numbers are odd, and they're always going to be odd, and we have a 5 in here, when I multiply all these numbers from here on out, I'm always going to get a units digit of 5, because that's what happens when you multiply odd numbers by 5. You always have a units digit of 5. And what am I doing? I'm always adding 2 to that number. So even if I multiply all these numbers, I'm still going to get it ending in 5 and then have to add 2 to it. So my first units digit will always have to be 7 from here forward, no matter what. because I'm always going to get a number that ends in 5 because of this number right here. So 7 has to be the units digit of the 2025th term. Remember, look for patterns on problems like that where they're making you look way off into the future. All right, number 194. If 4 distinct positive integers sum to 20, how many such choices of positive integers without regard to order include at least one integer that is divisible by 5? Okay, so I've got 4 numbers. It says they're distinct and positive, which means none of them are the same, and they're all positive numbers. Now I want at least one of the numbers to be divisible by 5. Well, I got 5, 10, 15, and 20. I can't use 15 or 20. If I make this number 15, then these numbers would have to be like 1 plus 2 plus 3. Those are the smallest numbers possible. And that would give me 21 instead. So I can't use 15. I definitely can't use 20 because then I wouldn't get numbers that add up to 20. So I only have 2 cases that might work here. Case 1 has the first number here as 5. And then I have to add 3 numbers together to give me the other 15 that I need to be 20. All right, so let's start with the smallest numbers possible. 1, 2, I'm trying to get to 15. So 1, 2, and 12. There's one case that would work, 1, 2, and 12. Then I'm going to do 1, 3, and 11. Everything's great. Then I would do 1, 4, and 10. Things are still going great. Doesn't this feel good? Then I would do, I can't do 1, 5 because I've already got a 5 here. These have to be distinct numbers. So maybe I would try to do 1, 6. I would get 1, 6, and 8. I am tapped out on starting with a 1 at this point because my next number would be 1, 7, and 7, and then I wouldn't have distinct numbers. So I've gone as far as I can go starting at 1. So now I'm going to move on to 2. 2, I can't start at 2, so the next number is going to be 3. 2, 3, and 10. There we go. We've got that one. Next one, I'd try 2, 4, and 9. So this adds up to 15. Yeah, everything's going well. Then I can't do 2 and 5 because then I already have a 5 up here. So maybe I would try 2, 6, and 7. All right. And I can't go 2, 7 because then I would have 6, and I've already done that one right here. Okay, then I would try 3. 3, 4, it's 12, 7, 8. So 5, 3, 4, 8. So all these numbers are adding up to 15. And then I might try 3, 5, but 3, 5 doesn't work because I already have a 5 here. Maybe I would try 3, 6, but that would be 3, 6, 6. I'm tapped out. I could try 4, but I can't do 4, 5. So I'd have to do like 4, 6. And then that would be 5. So no, I'm tapped out. This is as many as I get. I've got 1, 2, 3, 4, 5, 6, 7, 8 combinations here. So in total, I have 8. That's case 1. That's if my first number was 5. Let's do case 2. And my first number now is 10. Now what I have to watch out for is I have already counted some of them with 10 in it. I can't double count them now, so I have to be careful with that. So let's try 1, 2, and these have to add up to 10, so 1, 2, and 7. I didn't use that one up here because there's no 5s there, so that's good. Let's try 1, 3, and 6. That works. Then I would have 1, 4, and 5, but I can't use that because I've already got 1, 4, and 5 in this combination here, so I can't double count that one. I'm stuck. I would move on to 2s. 2, 3, and 5. Uh-oh, can't use that one. I already used that one in this combination here. I have done all the combinations. From case 1, I have 8 combinations. In case 2, I've got 2. There are a total of 10 combinations that would work for this. Oh, new piece of paper. All right, number 195. A standard deck of cards has 4 suits: clubs, hearts, and spades, and diamonds. With 13 cards in each suit, Jairus deals 3 cards from a standard deck to David. What is the probability that David receives exactly 1 heart? All right, so there are 3 ways to do this. Either his first card is a heart, his second card is a heart, or his third card is a heart. So if his first card is a heart, there is a 13 out of 52 chance that his first card was a heart, because there are 13 hearts and there are 39 cards that are not hearts. Okay, his next draw, we're not going to have hearts. So his next draw, he has 39 not hearts to choose from, and he only has 51 cards left because he already drew a heart. On his next draw, we're not replacing these cards, so now he only has 38 cards that are not hearts, and now there are only 50 cards to choose from because he's already chosen 2 cards. So this is heart, not heart, not heart. Now, if I did another order and did the heart as the second card being drawn, here's what I would get. 39 out of 52. Then he would choose a heart. There's 13 hearts to choose from, but there's only 51 cards. Then he would choose a not heart. He already chose one of them, so there's only 38 not hearts left out of 50 cards. These three numbers in the numerator and the denominator are exactly the same as this up here. Now let's do our last one. What if he does not heart, not heart, heart? So that would be 39 out of 52. Then he would have 38 not hearts left out of 51 cards. And then he would have 13 hearts left out of 50 cards to choose from. Again, we've got the same 3 numbers in the numerator and the same 3 numbers in the denominator. So all I really have to do is take this product and multiply by 3, because these are all the same. So let's go ahead and do that. We can probably start by reducing. 13 goes into 52, and we get 1/4. 3 goes into both these numbers, so this is 13, and 3 goes into 51 17 times. This reduces here. We get 19 over 25. So now we're going to just be multiplying going straight across. Yeah. I mean, we can just use our calculator at this point, but whatever. So we're going to just multiply going straight across. I think when I originally did it, I just multiplied going straight across. Is that what I did? No, I didn't. I did it like this. Yeah, so this ends up being 247, because this is a calculator problem. You can use your calculator. 247 out of 1,700. And then there are 3 combinations that work. So we multiply this by 3, because all 3 of these have the same probability. And we end up with 741 out of 1,700. Final answer. Yeah, you need the calculator on this one. All right, next one. Water costs $6.70 per 100 cubic feet. So for this one, we've got $6.70 per 100 cubic feet. To the nearest hundredth of a cent, what is the cost of a glass of water, assuming that the inner diameter of the glass is 2 inches and the height of the water in the glass is 5 inches? All right, so we've got a glass, the diameter, so the height is 5. The diameter is 2, so this is a radius of 1. So the volume of the glass is 5 times pi r squared. Pi r squared is just pi, so this is 5 pi. So the volume is the height times pi r squared. Height's 5, r is 1, so it's 5 times pi, which is 5 pi. So that's my volume. Total volume, 5 pi. That's in inches cubed, cubic inches. All right, so now it is just a conversion problem at this point. We've got $6.7 over 100 cubic feet. And now we need the conversion of cubic feet to cubic inches. So in cubic inches, we've got inches times inches times inches. So if I want to convert cubic inches, there are 12 times 12 times 12 inches for every 1 times 1 times 1 cubic feet, right? So there's a total of 12 times 12 times 12 is 1728. There's 1728 cubic inches for every 1 cubic foot. Because there's 12 inches times 12 inches times 12 inches for 1 foot times 1 foot times 1 foot, because these are inches cubed. All right, so we can set up this proportion here, not proportion, this conversion. I would put 1 cubic foot in the numerator. Now the feet cancel. Over 1,728 inches cubed. Now we're in dollars per cubic inch. We can actually just kind of use the calculator at this point. So this answer would be in dollars per cubic inch. Or do I have to use, oh, I forgot. I still have to multiply by 5 pi. I don't want my answer in dollars per cubic inch. I want my answer just in dollars. So I'm going to multiply by 5 pi inches cubed. And now in my conversion, the inches cubed are gone. My answer now, when I multiply going straight across, will be in dollars. So if we take this, if we do, let's see, it's right there, yeah. So if we end up doing 5 pi times 6.7, we get that number. Then we're going to divide it by these two numbers. So I'm going to just do 172800. 172800. Oops, dang it. Divide by 172800. Here's what I get. Now this is in dollars. I get 0.0006. So here we want our answer in cents. So cents, this would be 600th of a cent. So our answer would be 0.06 cents. And there's our answer. All right, next one, 197. Man, this one's taking forever. Okay, what is the maximum value of n such that 4 to the nth is a factor of 120 factorial? Okay. 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 So here's what I'm going to do. I know that I'm multiplying a bunch of numbers. I'm going to find out how many 2's, how many factors of 2 are in 120 factorial. So let's start with multiples of 2. How many multiples of 2 are in 120? Well, 120 divided by 2, there are 60 numbers that are multiples of 2 in there. Now, that's not the only way I can get a 2. I can also do multiples of 4. Because this is 2 to the first. Now I'm looking for 2 to the seconds. Now, all of these multiples of 4 have already been counted here. So these are going to have one extra 2 in them. So I'm just counting the extra 2's that I'm going to get from having a multiple of 4. So 120 divided by 4 is 30. So I'm going to get 30 more 2's. These, remember, are already counted in this group. They just have an extra 2. So we're saying how many extra 2's do we have? All right, now let's try 2 to the third. 3 2's. Again, we have already counted these numbers. They were part of the previous ones. These have 3 2's in them, but the 2 2's have been counted here, and 1 2 has been counted here, so we're just counting the extra 1. So how many 8's go into 120? So when I look at the number of 8's that go into 120, I get 15. So that's how many extra 2's I get from 2 to the thirds that are in 120. Okay, still counting the 2's. Let's try 2 to the fourth. How many multiples of 16 are in 120? So I do 120 divided by 16. I end up with 7. Doesn't come out evenly, but we definitely have 7. We keep doing this. Multiples of 32. 120 divided by 32. We get 3. 64. How many 64's are in 120? There's only one. It comes out as a decimal, but there's only one of them. So this is the total number of 2's that are in 120 factorial. 60 plus 30, that's 90, 105, 125, 126. So I have 120, 90, 105, 106. Look at my calculator. I didn't do that right. 60 plus 30 plus 15 plus 7 plus 3 plus 1. 116. Okay, good. So I get 116 inside of there. So there's 116 2's inside of here. But I want to know how many 4's are in there. So it's similar to a problem that we did on warm-up 11. So I would just divide this by 2, and there would be 58 4's inside of 120 factorial. So our answer is 58. I almost talked myself out of that answer for some reason. I don't know. All right. Oh, almost there. Gosh. Let S be the sum of all positive integers less than or equal to 2026 that are of the form n squared plus 1 for some positive integer n. What is the remainder upon dividing S by 100? Oh, man. So I want all the numbers where I can get n squared plus 1 less than or equal to 2026. Now, we know that 2026 is 2025 plus 1. And if you've been paying attention at all, you know that 2025 is 45 squared. All right, so I have to go from 1 squared plus 1 up to 45 squared plus 1. So I want all of the perfect squares from 1 to 45. There is a formula for this. I didn't do it like that. I did it the long way and looked for a pattern, and I did find a pattern. Here's the pattern. So I started by saying, okay, I'm going to do 1. 1 squared plus 1 is 2. Okay, now I'm looking for a remainder when I divide by 100. So I'm going to look at the last 2 places because that'll tell me what my remainder is. So if I plug in 2, I get 4 plus 1 is 5. If I plug in 3, 9 plus 1 is 10. If I plug in 4, I get 16 plus 1 is 17. All right, I'm going to keep on doing this. 26. 36 plus 1 is 37. 49 plus 1, 50. 64 plus 1, 65. I'm going to run out of room. 81 plus 5, 82. And finally, if I plug in 10, I get 101. Okay, so I am only looking at the last 2 digits because I want to find out what my remainder is going to be. Quickly calculate this. It ends up, just looking at these 2 digits, it ends up being something ending in 95. So the last 2 digits add up to 95 as these digits over here. It's more than that, but these last 2 digits is 95. Now what I found is when I kept on going and did 11 through 20, I still got these repeating numbers where they came out to 95. And then when I did 21 to 30, the pattern, I assumed the pattern was going to keep going. I double checked it, it did. So 31 to 40 also got me to 95. So when I did 1 to 10, 11 to 20, 21 to 30, 31 to 40, I saw a repeating pattern that kept on giving me a remainder of 95 on all those. And now all I have to worry about is the numbers 41, 42, 43, 44, and 45. Luckily, this is a calculator problem. We can quickly plug this into a calculator, which I did. And I only looked at the last 2 digits. So these are the last 2 digits of this number. I got 82. See, ends in 2, ends in 2. It was a pattern that kept on repeating. I got 65, 50, 37, and 26. You can kind of see that there's a pattern, especially to the units digit. There was definitely a pattern that happened. Well, it has to be a pattern because we're squaring, whatever. These numbers here ended up being 60, just looking at the last 2 digits. So what did I do? I did 3 times 95 and then added 60 to it. So I got 380 plus 60. That comes out to the last 2 digits being 40. And that's what the remainder would be when 100 goes into there. Like I said, there is a big old equation. I don't see how you're going to memorize it. Maybe you will. You guys would probably memorize it. Look it up. There's an equation for adding together all of the perfect squares. Definitely is. So you can do that and then figure out how many times that you have to add 1 to it. So the other way to do it is find the formula that adds all the perfect squares from 1 to 45. So the sum of the perfect squares from 1 to 45. So find all those perfect squares, but then you're adding 1 45 times. So when you find the sum of that, you'd have to add 45 to it. Like I said, I did it like this. It actually didn't take me that long to do it the long way here, especially when I noticed there's a pattern to it. But whatever. I don't think this problem's fair. We get 40. Okay. Almost there. All right, in convex quadrilateral ABCD, the area of triangle ABC is 20. The area of triangle ACD is 18. And the area of triangle BCD is 25. What is the area of triangle bad? All right, so here's what I'm going to do. I'm going to label these little a, little b, little c, and little d. So ABC, that would be a plus b. A plus b needs to be 20. And then ADC would be d plus c. And that would equal 18. Now notice between these, I've got A, B, C, D. I've got all 4 letters right there. So adding these two together, I've got A plus B plus C plus D equals 38. All right, and then I've got BCD, that's BCD, that's this one over here. That's C plus B. That's those 2 sections right there. That's equal to 25. I want BAD. BAD is A plus D. That's everything except for this one. So what I can do is I can subtract this from this equation here. I can subtract C minus B equals negative 25. The C's cancels, the B's cancel, and then 38 minus 25 ends up being 13. So A plus D equals 13. And A plus D is triangle bad that I'm looking for. So my answer is 13. John and Tim each flip a fair coin 4 times. What is the probability that John obtained the same number of heads as Tim? Express your answer as a common fraction. Okay, so they flip coin 4 times. What's the probability that they get the same heads? Okay, so when you flip the coin 4 times, there's 2 to the 4th combinations. There's 16 combinations. So let's look at the ways that we could do this. We could get no heads. We can get 1 head, 2 heads, 3 heads, or 4 heads. So the probability of getting no heads, that would be head, head, that would be tail, 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 tail. There's only one way to do that. 1 out of 16 possible ways to do it. What if we do 1? If you have 1 head, then there are only 4 ways to do that. Head, tail, 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 head, tail, 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 head, tail, head, 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 tail. So there's only 4 ways out of 16 to do that. And that's going to be the same probability as this one over here, 4 out of 16. And this would also be 1 out of 16, because then you would just look for tails instead of heads, and you could still see those combinations. So I've got 5 and 5. That's 10 combinations out of 16. That means I have 6 combinations out of 16 for this one. All right, so those are all my different combinations. And now I just need to find out what's the probability that they get the same number as each other. So if the first guy does this one, the second guy has a 1 in 16 chance of also doing that. So the probability of him doing it, then him doing it, that would be 1 out of 256. If the second guy were to get 1 head, that would be 16 out of 256. If the other guy were to get 2 heads, he has a 16 out of 16 chance. So for both of them to do it, the probability that they both do it would be 36 out of 256. And then these numbers are all the same, 16 out of 256 and 1 out of 256. All right, so if I add up all these numbers, 17 plus 17 is 34, 34 plus 36 is 70. I get 70 out of 256, which reduces to 35 out of 128. That's my final answer, and I'm sticking to it. So my final answer, 35 out of 128. The end. Gosh, that went forever. Sorry about it. Bye-bye.